Hi all, welcome to the lecture on heat exchangers. This is the fourth module of the course Heat and Mass Transfer. In the first two modules, we have studied two modes of heat transfer, namely conduction and convection. This topic, that is heat exchangers, is actually an application of these two modes of heat transfer. So, what is a heat exchanger? A heat exchanger is a device in which heat is transferred between two fluids at different temperatures without mixing each other. That is, it is transferred from a hot fluid to a cold fluid. Heat exchangers have variety of applications, from household equipments like air conditioners, refrigerators, to chemical processing and power production in large plants. These are some examples of heat exchangers: condensers and evaporators in a refrigerator. This example you are all familiar: automobile radiators, intercoolers and preheaters. All these are the examples of heat exchangers. Now, we move on to the classification of heat exchangers. The broad way of classification is based on the nature of heat exchange process. There are basically two types of heat exchangers based on the nature of heat exchange process. First one is direct contact heat exchangers. The other one is indirect contact heat exchangers. In direct contact heat exchangers, both fluids, that is hot fluid and cold fluid, both are immiscible fluids and it will contact directly in a chamber. This figure shows a direct contact heat exchanger, in which the water is sprayed into the form of droplets to the downward motion and the air is moving up in the upward motion. During this motion, the heat will transfer between these two fluids. If water is hotter than the air, then heat will transfer from water to air, or in the other way. Okay. The best example of this type of heat exchanger is cooling towers exchangers. The other classification is indirect contact heat exchangers. In this, both fluids doesn't contact each other. These are two types. There are two types of indirect contact heat exchangers. One is regenerators and the other one is recuperators. Okay. So the first one, regenerators. It is also called a storage type heat exchanger. You can see a storage type heat exchanger here. Actually, the hot and cold fluid flow alternately. This is very important. In this type of heat exchangers, the hot and cold fluid flow alternately through a porous medium called matrix. So, during the flow through the matrix, hot fluid stored its heat into the matrix. See, these are two valves. If when the hot fluid flow through the matrix, these two valves will be closed. Okay. So first, hot fluid will flow through this. During the flow through the matrix, hot fluid stored its heat into the matrix. Then, after that, we will close these two valves and open these two valves. So the cold fluid pass through the heated matrix and extracting the heat from it. So this is important. The hot and cold fluid flow alternately through a porous medium, that is matrix. So the example for this type of heat exchanger is air heater of blast furnace. Air heater of blast furnace. Then this is the most popular heat exchangers. We are going to deal this heat exchanger only in this module. Okay. Recuperators or direct transfer type heat exchanger. Okay. So here in recuperators, the hot and cold fluid flow simultaneously on either side of a separating wall. Okay. So there is no physical contact between hot and cold fluid. There is a separating wall in between. So heat transfer consists here, as we can see a figure here. This figure shows actually a tube-in-tube heat exchanger. Tube-in-tube heat exchanger or double pipe heat exchanger, whatever you can say. In this, the hot fluid passing through the inner tube and the cold fluid is passing through the outer tube or the annular spacing of the outer tube. Okay. So both the fluids doesn't contact each other. Okay. There is no physical contact between. If this is hot and this is cold fluid, heat will transfer from this hot fluid to the cold fluid. Okay. To this separating wall. Actually, the inner pipe is the separating wall in this type of heat exchanger. So there are the heat transfer consists convection between hot fluid and the tube surface, inner surface of the tube. Then the conduction heat transfer through the wall thickness, through this inner pipe thickness, and the convection heat transfer between cold fluid and the outer surface of the inner tube. Okay, so these three modes, actually three heat transfer modes happening here: two convection heat transfer and one conduction heat transfer. So these are the examples for recuperators or direct transfer type heat exchanger: automobile radiators, condensers, superheaters. All these are examples of recuperators or direct transfer type heat exchanger. This is a second classification based on the relative direction of fluid motion. Based on the relative direction of fluid motion. There are three types actually: parallel flow heat exchanger, counter flow heat exchanger, and cross flow heat exchanger. Okay. We can see in a parallel flow heat exchanger, both fluids, hot fluid and cold fluid, enter into the heat exchanger at the same side and move through same direction in the heat exchanger, and it will move out from the heat exchanger at the other end, same end. Okay. So because of this, it is called parallel flow heat exchanger. Both fluids moves in the same direction. Okay. So the flow of fluids is unidirectional and parallel to each other. This figure shows the temperature profiles of hot fluid and cold fluid. As we can see from the figure, the hot fluid loses its heats from inlet to exit, and the cold fluid gains heat from inlet to exit. Okay. So this is the second type, counter flow heat exchanger. Counter flow heat exchanger. This, the both fluids enter into the heat exchanger at the opposite sides. Okay. and it will moves in the opposite direction. Here you can see the hot fluid enter into the heat exchanger at this end and moves in forward direction through the inner tube, but the cold fluid enters into the heat exchanger at the opposite side and it will moves in the opposite direction and exit at the other side. Okay. For a given, here you can see this is the temperature profile of the counterflow heat exchanger. The hot fluid enter at this side and loses its heats during the flow through the heat exchanger and exit at this side, but the cold fluid enter at this side and gains heat during the flow in the opposite direction and it will move out. So you can see from the both temperature profiles, in parallel flow heat exchanger, the exit temperature of cold fluid, this is the exit temperature of cold fluid, the exit temperature of cold fluid is always less than that of the hot fluid. The limiting case, in this case, the limiting case is both the fluid's exit temperatures will be same. Okay, this will move, but the limiting case is will be same. The exit temperatures will be same. But in counterflow heat exchanger, the exit temperature of cold fluid, that is this one, exit temperature of cold fluid may be higher than that of hot fluid. Okay, this is the exit temperature of hot fluid. This is the exit temperature of cold fluid. Here in counterflow heat exchanger, there is a chance. Okay, the cold fluid exit temperature will be more than that of the hot fluid's exit temperature. This point, please keep it in mind. The next type of heat exchanger in this classification is cross-flow heat exchanger. There are two types of cross-flow heat exchanger. Actually, the cross-flow heat exchanger is a heat exchanger in which both fluids are directed at right angles to each other. Here you can see in both figure, one fluid moves through this direction and the other fluid moves right angles to that direction. Okay. So there are two types of cross-flow heat exchanger. One is both the fluids unmixed and the other one is one fluid mixed, another fluid unmixed. See, in both fluid mixed type of heat exchanger, we have some baffles or plates, parallel plates arranged here. So the fluid in this direction will not mix each other. Okay, it will pass through the spacing between these plates, and the other fluid is passing through these tubes. So that fluid also will not mix each other. Okay, so both fluids unmixed. In this case, you can see the fluid which is passing or flowing through these tubes will not mix each other. One fluid unmixed, but the fluid which is passing through this direction can mix within the space anywhere. Okay, the fluid layer passing through this bottom side can mix with the fluid particles moving through the top side. Okay, at somewhere in the space. Okay, so one fluid mixed and another fluid unmixed. Okay, so this is another type of classification: parallel flow heat exchanger, counter flow heat exchanger, and cross flow heat exchanger. Okay. Then the next classification is based on the design and constructional features. Design and constructional features. So basically, it is shell and tube heat exchanger. Okay, there are different types of shell and tube heat exchanger. This figure shows a one shell pass and one tube pass heat exchanger. In a shell and tube heat exchanger, actually there is a shell. So you can see this is a shell. Okay, and there are bundle of tubes arranged parallelly within the shell. Okay, you can see 1, 2, 3, 4 tubes here, but it is not actually 4 tubes, it is bundle of tubes. Okay, so one fluid will move through these tubes and the other fluid is moves through this shell space. Okay, so here you can see two headers, one front end header and rear end header. Actually, the the fluid moving through the tubes is entering here on the front end header and moves through the tubes and will exchange heat with the shell side fluid, and it will exit at the other header. Okay, with outlet. And you can see on shell side the other fluid enter on this side and passing in the opposite direction. So you can see this is a counter flow heat exchanger. Actually, this is a counter flow heat exchanger. Both fluids moving in the opposite direction. Okay, here you can see some baffles in between. So these baffles actually use it to ensure the zigzag motion of the shell side fluid, which enhances the heat transfer rate by exploding more contact with tube surfaces. Okay. So it will enhance heat transfer because of this zigzag motion. Okay. So this is one shell pass and one tube pass. This is over here. The both fluids moves along the length of the heat exchanger. This is the length of the heat exchanger actually. Both fluids moves along the length of the heat exchanger only once. Here you can see the shell side heat exchanger tube is entering at this side, moves through the length of the heat exchanger and exit at the other side. So it will move only once through the length of the heat exchanger. So it is one shell pass, and the tube side heat exchangers, tube side fluid is enter at this side and exit at this side. During this movement, it will move through the length of the heat exchanger only once. So it is one tube pass heat exchanger. So one shell pass and one pass heat exchanger. Okay. There are other arrangements, multi-pass flow arrangements. You can see here one shell pass and two tube passes. It can be 2 tube pass, 4 tube pass, 6 tube pass, 8 tube pass, and so on. Okay. So here you can see on shell side the fluid is entering through this side and moves through the length of the heat exchanger only once and exit here. So it is one shell pass. But you can see on tube side the fluid entering at this side moves through the length of the heat exchanger on this direction once, then it will moves in the opposite direction along the length of the heat exchanger. So it will move 2 times through the length of the heat exchanger. So it is called 2 tube passes. Okay. So this is another type, 2 shell pass and 4, 8, 12, 16 and so on. Okay, 2 shell pass and 4 tube pass heat exchanger, shell and tube heat exchanger. You can see the shell side fluid enter here and it will move on this direction first, then it will return back to this direction and it will enter at the same side, exit at the same side. So 2 shell pass, and you can see 1, 2, 3, 4 tube passes here. It can be 4, 8, 12, 16 and so on. Okay, 2 passes. So this is the another type of classification, and the other type classification, final classification is according to the physical state of fluids. According to the physical state of fluid, it can be condensers and evaporators or boilers. Okay, so in condensers, in both of this type of heat exchangers, physical states, one fluid having phase change and the other fluid do not have phase change. Okay, in both condensers and evaporators. In condensers, hot fluid having phase change process. Okay, here the cold fluid extracting heat from the hot fluid. So because of that extraction of heat, the hot fluid, that means it is a gas. Okay, the gas loses its heat or latent heat, and it will change its phase to liquid. Okay, so this is a condensing fluid. So this is a temperature profile. Actually, this is the temperature profile. In this temperature profile, you can see during phase change the temperature is constant. Okay, so in condenser, the hot fluid is having phase change process, so its temperature is constant throughout the length of the heat exchanger, and the cold fluid gains heats and its temperature will increase continuously from inlet to exit of the heat exchanger. Okay. In evaporators or boilers, cold fluid is extracting heat from the hot fluid and getting phase change process. Okay, so here the cold fluid temperature is constant throughout the length of the heat exchanger, and the hot fluid loses its heats from inlet to outlet. Okay. So these are the main type of classifications in exchangers. Okay. Now we move on to the analysis part of heat exchanger. So for the analysis part, first we consider the surface areas of a heat exchanger. So here in this module, we are dealing only recuperators. Okay, so indirect contact heat exchanger, recuperators only. Okay, so if we take a tube-in-tube heat exchanger, you can see there are two surface areas. One is the outer surface area of the inner tube, and the other surface area is the inner surface of the inner tube. Okay, the hot or cold fluid will pass through this inner side of the inside tube, and the other fluid moves through flowing through the angular space in between these two tubes. Okay, so actually the heat exchanger areas are inside surface area of the inner tube and outside surface area of the inner tube. Okay, so if this is a tube of diameters, inside inner diameter di and outer diameter do, then These are the inner area. This is the outer area. Pi d L. Pi d0 L is the outer surface area. Pi d I L is the inner surface area. If the hot fluid moves through the angular space and cold fluid moves through the inner tube, then it will transfer from the hot fluid to cold fluid in this direction, in this radial direction. Okay, so these are the surface area of heat exchange process. Okay, area of heat exchange process. So this is actually the area of the heat exchanger. Okay. Now we have already discussed the thermal resistance network concept in the first and second module. Okay. So during the same, if we take the same example, there is a tube-in-tube heat exchanger. If the hot fluid is passing through the inner tube and the cold fluid is passing through the angular spacing, this is that inner tube. Okay, a heat is passing or heat is transferred from the inner side of the inner tube to the outer side in radial direction. Okay, so here you can see there are three modes of heat transfer here. One is convection heat transfer between the hot fluid. In this case, in this example, hot fluid to the inside surface area of the inner tube, and then the conduction heat transfer through the thickness of the inside tube, and there is another convection heat transfer from the outer surface of the tube to the cold fluid in this case. Okay. So we can say there are three resistances of heat exchange process here. One is convection heat transfer. If the temperature of the hot fluid is Ti and the outer cold fluid is To, then this is the network, thermal resistance network. There are the convection resistance here, that is Ri, and the inside tube we have a convection resistance 1 by HiAi. Okay. And we have a conduction resistance here, R wall, because it is a tube. The equation for the cylindrical coordinate, that is ln of R 2 by Ri divided by 2 by KL, that is R wall here, and outside resistance is convection resistance is 1 by H0 K0. Okay, sometimes it will be helpful. Okay, so next, as we already said that there are multiple modes of heat transfer in a heat exchanger. Okay, so two convection heat transfer process and one conduction heat transfer. Okay, so on either side of the separating wall we have convection heat transfer, and to the thickness of the across the wall we have conduction heat transfer. Okay, so it is convenient to work with the overall heat transfer coefficient in case of heat exchangers. Okay, so your equation will be heat transfer equation in a heat exchanger will be UA delta T, where U is the overall heat transfer coefficient and A is the area of heat exchange process. In this case, it is surface area of the heat exchanger. And delta T is the temperature difference between the hot fluid and the cold fluid. Okay, so this equation we have already studied in the first module, conduction. Okay, so overall heat transfer coefficient equation you can see here. In a tube-in-tube heat, if it is a tube-in-tube heat exchanger, we know that the area of heat exchange process is increasing continuously in radial direction. At inside, the area is lesser than that of the outside surface area of the heat exchanger. So, we may have two overall heat transfer coefficients depending on which area we are considering. Okay. If we consider the inside area, then we will get a inside overall heat transfer coefficient. Okay. If we consider the outside area, we will get outside overall heat transfer coefficient here. Here you can see the equation for overall heat transfer coefficient. Okay. This equation also we have derived in first module. Okay. Ui is equal to 1 by hi plus ri by k ln of r0 by ri plus ri by r0 multiplied with 1 by ho. Okay, where r0 is the outer radius of the inside tube, ri is the inner radius of the tube. Okay, hi is the inside transfer coefficient, ho is the outside transfer coefficient, k is the thermal conductivity of the separate wall. Okay, here you can see the outside overall heat transfer coefficient equation. Okay, in the same way, both these equations we have derived in the first module. Okay, so here you can see, you can say UiAi should be equal to U0 A0. Okay. Delta T is the temperature difference between the hot fluid and cold fluid. Okay. If we take the resistance equation, we have AI on both sides. AI. Okay. So this is the total resistance. This is the inside resistance. This is the wall resistance, conduction difference resistance. This is the outer convection resistance. Okay. So next one is fouling factor. Okay. Actually, if the heat exchanger is working in long time, there is a chance for the accumulation of deposits on the heat transfer surfaces. Okay, this accumulation of deposits is called fouling. Okay, these deposits will be at the inside surface of the tubes or heat exchanger and outer surface of tubes on both sides of the heat exchange surface area. Okay, actually this accumulation or fouling is an additional resistance to heat transfer. Actually, it will deteriorate the heat transfer rate. Okay, because this is an additional resistance. Okay, the net effect of these accumulations on heat transfer is represented by fouling factor, which is denoted with RF. Okay, it is a measure of thermal resistance increased by fouling. Okay, so obviously for a new heat exchanger, the fouling factor is low, but it will increase with the time as solid particles build upon the heat exchanger surface. Okay. Actually, the fouling factor depends on these three factors: operating time, temperature, and velocity of the fluids. The first two times, operating time and temperature, will be directly proportional to the fouling factor. If the operating time increases, the fouling factor increases, and also if the temperature of the fluids at a higher level, then the fouling factor will be higher. Okay, but if the fluids move faster through the heat exchanger, then the fouling factor will be decreased. Okay, there is not much fouling takes place if the fluid moves faster. Okay, or velocity of the fluid is higher, then the fouling factor will be lesser. There are three types of fouling occurs in a heat exchanger. There are precipitation of solid deposits, then corrosion stands to occur corrosions. Okay, corrosion and other chemical fouling and biological fouling like growth of algae. Okay, so this, if we consider this fouling factor, this actually offers additional resistance to the heat exchange in the heat exchanger. Okay, so it will deteriorate. So in the equations of overall heat transfer coefficient, we consider this fouling at the inner surface and outer surface, you will get the equation of inner surface overall heat transfer coefficient and outer surface overall heat transfer coefficient, like this. Okay, these equations is you can found from the data book, page number 164 and 165. Okay, in page number 164 you will get a table. There are some values of overall heat transfer coefficient they given directly, and you can see these equations in page number 165. Okay. The next term is logarithmic mean temperature difference. Which we can see, we know that the heat transfer equation is UA delta T. Okay. This delta T is actually the temperature difference between hot fluid and cold fluid. Let's take a parallel flow heat exchanger. Okay. So this is the temperature profile of a parallel flow heat exchanger. You can see the hot fluid temperature decreases continuously from inlet to outlet. At the same time, the cold fluid temperature increases continuously from inlet to exit. Okay. If we take the inlet section of the heat exchanger, the temperature difference at the inner section is largest one. At the exit, it will be lesser one. Okay. In between, you can see the temperature difference decreases continuously. Okay. The temperature of hot and cold fluids varies along the length of the heat exchanger from inlet to outlet. So hot fluid temperature decreases and cold fluid temperature increases along the length of the heat exchanger. So temperature difference vary point to point from inlet to outlet of the heat exchanger. So which temperature difference we will take in this equation? So it is convenient. Okay, it is convenient to work with an average or mean temperature difference here. Okay, which is called logarithmic mean temperature difference. Okay, logarithmic temperature difference is actually an equivalent mean temperature difference between the two fluids for the entire heat exchanger. Okay, it will actually defined as LMTD, logarithmic temperature difference is defined as that temperature difference which, if constant, would give the same rate of heat transfer as actually occurs under variable conditions of temperature difference. Okay. So give a constant heat transfer rate throughout the heat exchanger. Okay, actually at inlet the heat transfer will be more, and at the exit the heat transfer between the hot fluid and cold fluid will be less in real case. So we should consider an average or mean temperature difference here. So that is called logarithmic temperature difference. The magnitude of the temperature difference at the locations will vary along the length of the heat exchanger. Okay. So it is convenient, it is important to take logarithmic mean temperature difference during the analysis, for the analysis of heat exchanger or for calculating the heat transfer rate to a heat exchanger. we know that the temperature difference between the two fluids decreases from delta T1. Delta T1 is the inlet temperature difference and delta T2 at the outlet temperature difference. Okay, so from inlet to exit, this temperature difference will decreases continuously. So it is tempting to use arithmetic mean temperature difference, which is the average of these two temperature difference at inlet and exit. Okay, delta T AM is arithmetic mean temperature difference AMTD, delta T1 plus delta T2 divided by 2, where delta T1 is the temperature difference between hot fluid and cold fluid at inlet. Delta T2 is the temperature difference between hot and cold fluid at exit of the heat exchanger. When delta T1 differs from delta T2 by no more than 40%, the error in using the AMTD is less than 1%. But this error increases to undesirable levels when these two differs greater amounts. That is, delta T1 differs from delta T2 by more than that of 40%, then the error for calculating AMTD or calculating the heat transfer rate will be more. Okay, so also you can see the delta TLM, that is logarithmic temperature difference, logarithmic mean temperature difference. So always less than that of arithmetic mean temperature difference. Therefore, using delta TAM in calculations instead of delta TLM will overestimate the rate of heat transfer in a heat exchanger between the two fluids. So we should take logarithmic mean temperature difference always for the analysis of heat exchanger or to determine the rate of heat transfer in a heat exchanger. Always we should consider the logarithmic mean temperature difference. Okay. So in the analysis part, we will consider, we will derive the equation for logarithmic temperature difference for both the parallel flow heat exchanger and counter flow heat exchanger. So the analysis part we will see in the next part of this lecture. Thank you all.